All right, welcome everyone. Let's talk now about BERT-based evaluation of text generation systems. The talk today has three parts. In the first part, that's about contextualized embeddings, and I will go very briefly through that because we basically know almost everything from this part already. So this is basically just a rehearsal or repetition of what we already know. Then I will also talk about reference-based evaluation, but also there you've already seen the you've already seen the video on mover score, so this will also be very brief. And then the final part, this is the novel part for today's talk. This is about reference-free evaluation with BERT. So about embeddings, we have seen a lot about static embeddings. So these are vector representations that are derived from neural networks. They were popularized in around 2013, 2014 by the Word2Vec model by Thomas Mikolov. After that, there have been very many extensions proposed, out of which we have seen uh, a, like a selection of very interesting ones, such as dependency-based embeddings, where the idea was that we change the context rather than a linear context to the left and to the right. We take the context given by the dependency trees. Then we've also seen fast text, which works more on character level, and we have, for example, seen multilingual embeddings, which embed words from different languages in a shared space. So all of those approaches that we've seen, initially they had one drawback. They had the principle that one word has only one vector, no matter in which context it appears. So you see here an illustration. So we have, for each word lives in a vector space, and the word has only one and the same vector, no matter where it appears. So then in 2018 came Elmo with contextualized embeddings, which was a revolution. So now words have different embeddings, different vector representations depending on their contexts. And this was really a major breakthrough. That's how the Elmo model looks like. You have a language modeling task. So you predict the next word or you predict previous word. You had two independent layers in this language model. And then depending on which position the word had, it would of course get a different vector representations, and you would concatenate those vector representations together with a static representation to get a final vector representation for this word happy here, for example. So the problems with Elmo were or are that it's a shallow model, it has only those two hidden layers, and it uses recurrent neural networks. So it was very quickly outdated by BERT. BERT replaced the recurrent neural network with transformer blocks. It was a much deeper network which had either 12 or 24 layers, and it does not add the embeddings as features, but instead it works in the paradigm of pre-training on fine-tuning, meaning that you will not use the BERT embeddings and plug them into your architecture, but you will just fine-tune the BERT architecture. So which again was a major revolution. So it's illustrated here. During pre-training, you have two tasks, namely one is masked language modeling, where some of the input tokens are masked, and the goal of the language modeling is to predict those missing tokens. And then there is another task, which is next sentence prediction. So from the current sentence, you predict the next sentence. So you have these two tasks. And with these two tasks, you train on a lot of data. You get very good initialization of your network. And then afterwards, once you have your network is initialized, you transfer all of the knowledge that you have learned on the general data to specific tasks, such as natural language inference, named entity recognition, or question answering, by just plugging a linear layer or some linear layers on top of the BERT network. And this is what we call fine-tuning. So because BERT was such a major success, again, we have seen many extensions of BERT. One of them was Roberta, that has been trained for longer on more data and removing and removing the next sentence prediction task. So that came about in July 2019. Then another issue of BERT is that it is very inefficient. So it's a very big architecture, has been trained for long, and if you want to fit that in your memory, that can get a problem. So people try to scale down BERT, and one of these attempts is Albert. It's a little bird, so that is a much smaller bird that can be trained and also fine-tuned much more efficiently. Multilingual BERT is another extension that is use BERT across multiple languages, not only English, and that has been provided in 104 languages. And there are many other extensions, some of which are shown in this picture here, which we could call a phylogenetic illustration of the genesis of BERT, let's say from Elmo, and also the other models that BERT has inspired. Good, so this was all about embeddings. Let's quickly repeat or recapitulate what we know about bi- and multilingual embeddings, which are also known as cross-lingual embeddings. Here the idea is that you have that similar words or maybe similar language, depending on which linguistic hierarchy you are working on, across two or more languages should be close in the vector space. This is illustrated here in a German-English vector space, where you see, for example, that Vater and man, which are words in different languages in German and English, are close in the vector space because they really are cross-lingually similar words, right? So how could we induce those embeddings? We have mainly seen what people call offline methods. So these are, what you do there is you first compute embeddings in each language independently. So you compute embeddings for German, you compute embeddings for English, and you compute embeddings for French independently without any cross-lingual signals, and then you use a dictionary to map those independent spaces into a shared space, right? And we have seen a couple of methods in this paradigm. For example, we have seen the method of Mikolov. Then also Michael Artexte has done quite influential works in this area. Then in contrast to that, there are so-called joint methods, which directly at training time leverage bilingual data. So you use parallel, you use dictionaries, or you use parallel sentences. Parallel means they are meaning equivalent sentences in different languages. You leverage them directly while you train your models. And one such model is, for example, laser, also done by Michael Artexte and Holger Schwenk. And then there's a third category which does not really have a name. I call them now silly methods. You could also just call them naive methods, which multilingual BERT is an example, for example. And there you have you just take all of your data in multiple languages. So for example, you take Wikipedia in German, English, French, and you just concatenate those into one big file, and then you train BERT on that. So in this way, the words are also in a shared space, but you really do not have any bilingual signal. So you do not know that the words are which words are translations of which other words. So you will get vector representations, but you really have no guarantee that those vector representations for cross-lingually similar words, such as man and Vater and man, you have no guarantee that those representations will be similar, because you do not use any parallel data at training time. So these are basically three approaches that could be used to induce such embeddings. Good, let's come to the second part of the talk, reference-based evaluation with BERT. So this is also something that we've already seen in previous talks, in previous lectures. The idea is that you have a metric, and this metric takes two ingredients, y and y prime. And what is y prime? Y prime is a human reference, so this is a translation, or let's say this is a string, a sequence, a sentence that a human has produced that should be the correct that should be the gold standard translation or gold standard summarization, or depending on which area of text generation evaluation you are. Then you also have a system prediction. This is typically also a sentence or a summary or something like that, right? So this is produced by a system, and the metric M um, should evaluate how close these are, right? So it should say, are these very similar or are these very dissimilar? And the classical metric is based on n-gram overlaps. So in summarization, that would be rouge. In machine translation, that would be blue. And n-gram overlap means it just counts, or it just looks at whether specific words occur in both the system prediction and the human reference, or generalizing from words sequences of like n words, right? So we can look at an example. So let's say the input x, which we have ignored for the moment because our metric m does not make any use of x. The input x is a poem with 2 lines, and that input is who died 2 days before and now had found an unknown barren beach for burial ground. Then let's look at the human reference. Let's say some poet has produced this human reference, and the poet wrote, Vorgestern starben diese fand im Bette des fremden Sands die letzte Ruhestätte. So this is the gold standard produced by human. Let's say we have a machine translation system, and that is translating this input here into the following output. Der vor 2 Tagen starb und nun fand einen unbekannten öden Strand als Grabesstätte. So now our metric would take these 2 things into account, and it would compare these 2 things, and if it were blue, it would count the n-gram overlap. So now what we find here, that the n-gram overlap consists of just these 2 words which occur in both sentences, and therefore blue would probably say that this system prediction is not very good because it has only one match with the human reference. But we as human, we would probably say this is not such a bad translation. If we compare X to Y and we are bilingually fluent, we would say probably Y is not such a bad translation. And you could also see that it's doing paraphrasing of the, or it uses just equivalent words in many cases of the human reference. For example, vorgestern is vor 2 Tagen, okay. Then starb and starben, this is just morphological variation. Grabesstätte and Ruhestätte are also synonyms, right? So this prediction here is really not so bad. So how can we use soft metrics instead of hard metrics? So soft metrics, we mean we really take into account that words are similar and they don't have to be identical. So if we have such soft metrics, they can take into account lexical variation or paraphrasing. So we would use word embeddings, okay, that's cool, or we can use sentence embeddings for that. And of course, better than using static word embeddings, we would use contextual word embeddings. So now we already saw in a previous talk or in a previous lecture the mover score model. There's a similar model which is called BERT score. And that works as follows. It takes our 2 ingredients, namely the system prediction and the human reference. It feeds them through BERT. So for each word in the reference, for each word in the system prediction, we get a vector out, so a contextualized vector. And that could just be from some layer of BERT, or you take an average of all of the layers of BERT or something. So BERT has 12 layers or 24 layers. So each word has like 12 vectors or 24 vectors. You can average them, or you just take the representation in the last vector, in the last layer. So this thing here has 5 words. So we get 5 vectors. This here has 4 words. So we get 4 vectors. So we can do cosine similarities pairwise. So we compare everything with everything. So that's also illustrated here. We compare everything with everything, we do a cosine similarity. So we check what is the vector for it, what is the vector for the. We do the cosine similarity, it's 70% about, and we do this for all other entries also. And then this model, it constructs an alignment, and alignment between those two sentences, like a greedy or heuristic alignment. How does that work? Well, it says, for example, here are all the cosine similarities of this word the here to all of the words in the other sequence. So which one has the maximum, right? So it just takes the maximum here. So in each row it takes the maximum, and then after that, that gives a kind of an alignment between those two sequences. And then it says if the sum of those scores weighted by some other factor, so it introduces a few other factors also, like TF, IDF weights, if this says you something. So if those sum is high, if the best alignment is a good alignment, then the two sequences are very similar. And if the best alignment has a low score, then those two sequences are very different, right? So this is the postulate of this BERT score model. And and it's using contextualized embeddings in this way. Then our own work, the mover score paper that you have seen previously, instead of doing this heuristic or greedy alignment, it uses earth mover distance, where earth mover distance is the amount of work to be done to transform one probability distribution into another. So briefly illustrated here, you have two distributions, one given in red, one in blue, and then you have to check how much work do you have to do to transform those two probability distribution into one another, and that depends on the distance between the dots. How far are they away from each other, and how big are the dirt holes that we have to move, right? So these are the two ingredients, and you have seen a much more formal approach in the last lecture, so to speak. So I will skip that here. And then basically comes out the mover score. So we have the human reference and the system prediction. We feed them through BERT. We compute a similarity matrix or Euclidean distance matrix, which is more or less similar, not equivalent, but very similar. So we get our distance matrix, and in addition we get this transportation cost matrix, which says how much effort does it take to transport the different words one into another. And then we take those two ingredients, we sum them up, and we get our earth mover distance. So to sum up, the difference between BERT score and mover score is that BERT score is more heuristic. It uses this heuristic or greedy alignment, whereas mover score computes an optimal alignment by solving an optimization problem. Good. So these are the first two parts. Now let's come to the most important part of this lecture today. So this is the reference-free evaluation with BERT. So what is the problem, what we have seen so far with the reference-based evaluation? So the core problem was this human reference Y star, right? So some human has to produce this Y star. So this is costly. We have to pay some human to do that. And maybe, so if those humans have to translate a lot, it costs them more, they have to translate. And then also, the evaluation is limited to the parallel data available. So if you have 10,000 translations Y star produced by a human, then you can only evaluate on those 10,000 human translations, but not on more. So you do not really know whether your system performs also well on other domains, right? So if you evaluate just on news data, can you be sure that your system will also work well on Twitter data, right? So the question we ask ourselves is, can we get rid of the human references Y star and instead only use XY for evaluating text generation systems, where X is the source sentence? You have seen that before. That was for example, that was the two-line poem in English, right? The X. So we call this reference-free evaluation, abbreviated as RF eval. And like to sum up what what I've said in the previous slide is we want metrics that take in as inputs a sequence X and a sequence Y, where X is the source sentence or the source document, and Y is the system prediction, instead of having metrics that operate on Y prime and Y, where Y prime is the human reference. So we want to replace this one here by this one here. So now in the following, I will consider two sample tasks. The one is machine translation. So this is what the examples before were already about. So we have an input string, let's say in English, and we want to translate that into another language. And the other task that I will touch just briefly and marginally is summarization. And in particular multi-document summarization, where you have multiple documents on the same topic. So for example, they could all be on politics, and you want to summarize all of those many documents, let's say books on this topic, into one short summary. So these are the two model tasks. How can we do reference-free evaluation? So basically, we think there are two approaches, so the first one is we just directly, with some technique, assess the quality or similarity of X and Y. That's the first approach. And the second approach is we somehow are able to generate a pseudo-reference Y double star, and then go back to the standard reference-based case where we compare Y double star to Y. And in this case, Y double star takes the role of our original human reference, Y prime. So how can we implement each of those two? So the direct assessment, if we're in a multilingual space, or if we're in machine translation, we would use cross-lingual spaces, for example. That's an obvious solution. So we could use laser, that's what I've outlined before as a joint method, or we could use multilingual BERT, which I've already also described previously, or there are many others, like cross-lingual use, etc., etc. One of those cross-lingual spaces that we have available. In summarization, what we could do is we stay in a monolingual space. Usually summarization is just in one language, even though there are also other cases where people want to summarize in a different language. For example, for an English reader, it would be convenient to have a summary of Chinese web pages in English, of course, but the standard case is still that summarization is monolingual. But then you have those enormous length differences, right? Where you have an input that is very long because it may consist of thousands of documents which are all very long. And you have to compare those with one small human summary, right? So you have big length differences. Then the second thing, how could we do pseudo-references? Here are some ideas how to do that. I'm not going into those at all, not talking about them, but here's what you could do. You could use an external engine like Google Translate to generate a pseudo-reference. So you take your input sentence in English, for example. You use Google Translate to translate that into German, and Google Translate nowadays is very good. So that's high quality, and then you compare it to your system prediction. But of course, Google Translate is also very costly, right? That's a $1 billion project, so to speak. Or you could use something like unsupervised neural machine translation, right? We have already seen a very tiny little bit on that, but in principle you could generate a pseudo-reference using unsupervised neural machine translation. And in summarization, how would it look in summarization? What is a pseudo-reference there? One idea that we have explored in one of our recent papers is we could, for example, somehow determine which sentences are important in our source documents. Let's say we have 10 source documents, and we could somehow identify which sentences are more important than others. And we would only keep those important sentences. So we remove all of the rest and only keep the important ones. And then compare then we compare this one document that just contains the important sentences, and we compare this one document to our system summary, right? And how can we define the importance of sentences? Well, there are many aspects that play a role. For example, if you have news documents, the initial sentences are more important than the later ones. Then also maybe you can just, by the linguistic structure, identify certain sentences that have more important words, right? So there are many different ways how you could formalize this concept of importance. So let's briefly look into results, and let's do summarization first, and just very briefly, and then talk longer on machine translation. So so here is, we have different metrics here, and here we see how well those metrics correlate with humans, right? We have the Spearman correlation with humans. So we have three different setups here. The first setup is the reference-free setup, where we compare source documents to system predictions, so to system summaries. That's in blue. In red is where we have the costly human references, and in black will be the pseudo references. And in all three cases, we compare, of course, against the system prediction. So TF-IDF is basically, you do, well, TF stands for term frequency, IDF is for inverse document frequency. You just you make a TF-IDF statistic of X and Y. So basically, you extract those words that both are frequent but rare. So these are the frequent words, both in your input X and your system prediction Y. And then you compare those two distributions with one another. That's a very, very elementary baseline approach to solve that. That has already existed for a couple of years. And when we're in the reference-based setup, we could, for example, use Rouge, or we could use mover score, right? And what you see here, those reference-based cases are much better. They have much better correlation than TF-IDF. That's the first thing to note, and the second thing, mover is better than Rouge. That's already what we've seen in the earlier presentations. Then what we could do instead, we could use something like sentence bird. So there are a couple of people that have proposed a bird on sentence level, and what they do is they just, so if you have a sentence, and then if you apply bird to the sentence, you get, let's say if your sentence has 20 words, you get 20 vectors per time step. And or yeah, like you have 20 words, so you get you have the BERT model gives you 20 outputs, and each output contains multiple vectors, let's say 12 or 24 vectors at each output. So you could again do an average over all 12 or 24 layers, or you could just take the last layer. Let's say we take the last layer, and then to produce a vector representation of the whole sentence, you could just do an average over all those 20 or 30 sentences, 20 or 30 words that are in your sentence. And then you get a sentence representation based on BERT, right? And we could do that and then just calculate the cosine similarities. And what you see a little bit disappointingly, it's just on the level of TF-IDF, even below. So this is a little bit surprising, and very disappointingly is not a good solution. So what instead we could use is we use some fine-tuned BERT. Fine-tuned, for example, on semantic textual similarity, the task you already know. Maybe it should be good to recognize when two strings are similar, and we combine that with mover score. So this FBERT is the same as SBERT here. So those are the same, but now instead of doing cosine, we use mover, and you see now we're doing really better. So that really gives an improvement. But then finally, if we do the pseudo reference, we still can improve upon that, and so to speak, get a new state of the art. But you also see that there's a big difference between the reference-based case, which is also much more costly, so you cannot directly compare that. That's a cheap case, that's an expensive case. There's a big difference, but you may say you can live with this difference, given that this is here is much cheaper. But then also the question arises, why is there such a big difference? Well, maybe it's just difficult to get good pseudo references. Maybe this problem of selecting the important sentences is a difficult problem, and if we could solve that better, the gap here would probably diminish. Let's go into machine translation. Again, we have the three cases, but we ignore this one here. We did not explore the pseudo-reference case here. Again, we have PLU and MOVE in machine translation. Now there's a big difference. MOVE score is much better. Then let's see what we can do. We can apply laser. That's our sentence embedding technique. That is like the joint sentence embedding technique. We embed our source sentence and we embed our target sentence in different languages. We compute the cosine similarities. And surprisingly and also disappointingly, we are below PLU. But again, PLU is the more costly case, so this is the cheaper case, but we're still below that, so we are disappointed. If we use multilingual BERT and MOVE score, we get even worse. So now this is here even more disappointing, right? So we perform even worse than just laser and cosine. So where does that come from? So good question. So what we did is we take two steps. We do a remapping on multilingual BERT, because before I said multilingual BERT is such a silly model. It has no notion of cross-lingual alignments. So we do a remapping. That improves a lot. And then we add a language model to that, and you know what a language model is. So the language model basically just evaluates the why. So it says, is this a good English sentence or is this a good German sentence? We add this language model, and you see that we can outperform PLU. So in this case, in machine translation, we are really better than a strong baseline, namely PLU, which is also more costly, right? So we're satisfied to a certain degree with these results. And now let's talk about the remapping and the language model. So our suspicion is why the task did not perform well is because this MBERT is maybe misaligned. So if we would use laser, that's not misaligned, because laser was this joint model, right? And MBERT was this silly model. So maybe this silly model is misaligned. It doesn't know about translations, word translations in different languages. And the second thing that we have a suspicion is maybe these MT systems, machine translation systems, they often produce very little translation, so very literal translations. That is what we call translationese. So, and here's an illustration. Let's say you translate from German to English, and you have the German headline: Krankheitsfall, wann bezahlt der Veranstalter? Question mark. And then maybe a machine translation system would translate that as disease case when paying the organizer, which you already see is quite bad. So we probably have this, or not probably, this is a very common phenomenon of machine translation systems, that they are very literal. And then we ask ourselves, maybe these cross-lingual encoders do not properly handle these literal translations, these translationese, so to speak, and we will investigate this. But first, let's talk about the ill alignment. So the ill alignment of multilingual BERT is, so multilingual BERT hasn't seen any parallel data, so it doesn't know that Vater and father are translations of each other, so it hasn't seen any parallel data. So let's remap multilingual BERT. How do we do that? We take a little bit of parallel data from Europol, for example. That's the proceedings of the European Parliament translated in all of the European languages, and there we can easily get parallel data from. And then we learn a linear projection matrix similar to the approach of Mikolov. So basically, we want to remap our English space into a German space by learning this projection matrix W, and we minimize overall possible projection matrices, and then we get a remapping, right? And this XL and XK have vectors in two different languages, like German and English, and those vectors correspond to each other. So you have the vector of Vater in German and father in English. They are in the same row of the respective matrices, right? So, and you have seen that this remapping really does a good job. So this is really, we really identified this problem of multilingual bird. Now let's go for the second thing, the translation ease. So to do that, we do an analysis, and we can call this probing or fooling. So we fool our encoders. How do we fool them? So we have our Y prime, our human references. We can just randomly shuffle them. So we just get a random word order. So we want to test how do our metrics react to that. Then a second thing that we try out is we do an expert reordering. We take a human expert, and the human expert reorders the input sentence X into, the human expert reorders Y prime into the word order of the input sentence X. So they have the same order, more or less, if that is possible. So the first case, well, that checks basic properties, whether our cross-lingual encoders are bag of words models, so to speak. The second thing checks for translation ease to a certain degree, like very literal translations, but we can even go one step further with the literal translations, and this is the third case. So we do word by word translations of the input X. So we go over the first word, we translate that literally, we go to the second word, translate that literally, and so on. So all words, and we have then a word by word translation, and this is really this translation ease, right? So this is a case like given here. So let's look at an example. So we have the German input X. Dieser von Langsamkeit geprägte Lebensstil scheint aber ein Patentrezept für ein hohes Alter zu sein. Then we have the Y star, the human reference, given by an English expert who translated as follows: however, this slow pace of life seems to be the key to a long life. Then we have the random reordering. Well, that's just random, just randomly shuffle the words, right? Doesn't make much sense. To pay slow seems to be this life, etc., etc. The expert reordering is: this slow pace of life seems, however, the key to long life to be. What you see is the however moves into the middle, like in the German. Here the aber is in the middle. And to be moves in the end, which is very typical for German. You have verb final position in German, right? Verb second position. To be moves to the end. And then finally, a very literal translation. So this is already more literal translation of the input, but even more literal is a word by word translation. This von Langsamkeit of slow-paced, characterized lifestyle seems, however, a patent recipe for a high age to be. So these are the cases that we have here. Now we test our metric preferences. So we test what do our metrics prefer. And to do this test, what we do is, like now we produce many of those random reorderings, the expert reorderings, and the word-by-word translations. We produce many of those, let's say 50, 100, 300. And then we check what do our metrics prefer, and we check two metrics, laser and multilingual bird. And we feed in X and Y, the random permutation of Y star, and we compare. So we get a score out here, that's the score, and we subtract the other score for X and the original human reference Y prime here. So we want to check, so that's also a score. So now we subtract these two scores. This subtraction can be positive or negative. If it's positive, it means laser prefers the random reordering of Y prime over Y prime. And if it's negative, it means laser prefers Y prime over Y prime rand for fixed X, right? So, and now here we show the histograms. So this is overall our, let's say, 50, 100, 200, 300 cases. We see the values here are generally negative, so there are some positive, but the mass, the center is here clearly negative, which means that laser prefers Y prime over Y prime rand, which we find good because this means that laser is not a bag of words model and it really takes word order into account. Good. Same for multilingual bird, right? Again, clearly negative. Then we go to the expert reordered case, where we compare the expert reordering over the original input y star, the human reference. What we see here is the center is slightly positive or at 0. So basically that shows indifference. So laser doesn't care whether you have this expert, whether you have the expert reordering or the original human reference, which indicates that laser is indifferent between two orderings, namely the correct English ordering and like ordering where the source, which was German, and the target, which is English, have the same order, right? So it's indifferent between that. And for multilingual BERT, again, a very similar picture. So the center is at 0. Again, it seems to indicate indifference. Then we look at the word-by-word translations for laser. So here we put in word-by-word translations of X. And we see a clear preference. So the center is somewhere here on the positive side. So clear preference for word-by-word translations. And again, the same here for multilingual BERT. So what do we conclude? We conclude, and I have to say multilingual BERT, this is multilingual BERT plus mover score. So it's a combination of multilingual BERT and mover score. Whereas laser is laser embedded, so you embed the sentence with laser, you get a sentence embedding, and then you calculate the cosine similarity. So that's important. Those metrics are laser plus cosine and multilingual BERT plus mover score. So what we learned from that is that our metrics really have a preference for word-by-word translations, and so they seem to favor two things. If the input, if the source sentence and the target sentence have the same word order, that seems to be a good ordering situation for them. And the word-by-word translation have the additional benefit that they have very high lexical, cross-lingual lexical overlap. So because the words are really all there, right? So they're just there. It's not a direct lexical overlap because it's a language change, but all the words are there, while the human references do not always have this property. So some German words in the German sentence do not reappear at all in the English sentence because a human translator would take a more efficient translation, right? So these two things make word-by-word translations good for those cross-lingual metrics. They have two desirable properties: high lexical overlap in parentheses, plus a good word order. And those two things make them attractive from the perspective of those cross-lingual embedding spaces, such as laser and multilingual BERT. And therefore, those word-by-word translations get high scores by the metrics. And because machine translation systems tend to produce such word-by-word translations, then if we use our multilingual BERT or laser as a metric in the reference-free evaluation setup, then they will say, okay, these are good translations, and they will say those systems should be ranked very highly that produce such literal translations. But humans will not say that these are good translations, right? Because if we look at such a sentence down here, a human expert would not say that is a good translation of the original X, right? It would say this is a very this is a deficient translation produced either by a bad human bilingual speaker or by a bad machine translation system. So humans would rate that lowly, but those metrics rate it highly, right? So this is a main problem why these metrics do not work well. So to fix that, we did a linear combination of our cross-lingual metrics, such as multilingual BERT or laser or whatever. So we had the metric score, and we weighted that by 90%, but then we added 10% language model score. We just said how good is why a sentence in the English language, right? Of course, we could also add a language model for X, but our X, the input, we assume that this is already good, right? We don't expect usually that the input is also crappy. So there's nothing to place on X in our case. So, and once we've done that, you have seen the result before, then that really gives quite a nice boost of over, in this case, over 10 percentage points, right? Good. So this concludes this part of the lecture. So what we've seen is rapid advances due to evaluation metrics based on BERT, contextualized embeddings. This really helps a lot. And in the reference-free context, there's the reference-free evaluation, which is what we want to go for. There's still a big gap, but still we could beat, or the latest metrics even are able to beat strong reference-based baselines, at least for machine translations. And then we exposed, you can call this severe deficits of the current cross-lingual sentence encoders or metrics. Namely that while they're not bag of words models, they're indifferent between correct and source language word order, and they like this word by word translations, which we call translationese. And this poses really a severe problem for if you want to use those metrics for machine translation evaluation. I mean, on the one hand, it shows that those metrics have no deep understanding of language across two languages, because they have this preference for literal translation, and on the other hand, it shows you cannot really use those metrics reliably as metrics for reference-free machine translation evaluation. And with this I conclude, and here are the references of our latest papers that discuss exactly what I have presented today in this part of the lecture.